scalar tensor theory of gravity. And this is not original Lagrangian of the Brans-Zicke theory, but it's most general form of the Jordan Brans-Zicke theory. And you see that most important ingredient of this modification is the scalar field. What is a scalar field? Is it a real physical field? And people who work in particle physics should consider this field, like, for example, Higgs scalars, or this is just part of fundamental gravitational theory. This is the equations, and I don't discuss these equations in my talk, but of course we speak about scalar fields as about some new degree of freedom of the gravitational theory. And you can see that we consider additional scalar field. People consider the theory with several scalar fields and so on, but I will speak about just single scalar field here. And this is modified kinetic term, some potential term. And what is especially interesting and important, there is a term describing non-minimal coupling between scalar degree of freedom and tensor degrees of freedom. So coupling between scalar field and curvature. And this is some general form for Brans-Zicke theories, and you see that, and yes, I wrote here that usually a scalar field is minimally coupled with ordinary matter. People say that this is physical or Jordan frame, and scalar field is non-minimally coupled with the curvature. And please, I stress, I draw your attention to this term. Okay. In 1974, Hromdeski derived the most general action, which gives this second order equation of motion. And this action is more general action for scalar tensor theory of gravity, which give us the second order equation of motions. And in modern form, Kobayashi, Yamaguchi, Yokoyama give us the following Lagrangian, because the original Hromdeski Lagrangian is quite more complicated than this one. But this now is popular and modern form for Hromdeski Lagrangian. And you see that Hromdeski Lagrangian has 4 terms. 2, 3, 4, 5, it depends on the power of scalar field. And the Lagrangian has 4 arbitrary functions of scalar field, and x here is a kinetic term of scalar fields. So very, very big arbitrariness of this theory. But surprisingly, that the equation of motion of this quite general theory, equation of motion, are of second order. And what is interesting here, and I would like to draw your attention to the following fact. You see that we have various combinations of covariant derivatives of scalar field, nonlinear combinations, and so on. And only 2 terms describing non-minimal coupling between scalar field and curvature. This one and this one. This term looks like the Brans-Zicke coupling, like this one. And this term is new one. because this term describes non-minimal coupling between covariant derivatives of scalar field and curvature term, because G mu nu, it's the Einstein tensor. And indices means covariant derivatives here. So notice non-minimal coupling of the scalar field with curvature is provided by two terms. This is very general scalar tensor theory, and as subclasses of this theory, we can obtain not practically all known scalar tensor models. Of course, you can obtain Hilbert-Einstein action, non-minimal coupling, GR with the ordinary scalar field, K essence, KGB. I am from Russia, so it's some. I just can image when the authors of this paper was so excited. Oh, KGB. But it's not so funny. But anyway, KGB model, non-minimal kinetic coupling, very popular in maybe 10 years ago, Fab4, Galileons, and so on. You can obtain all known scalar tensor models as a subclass of the Horndeski theory. Well, moreover, you can still extend the Horndeski theory and obtain models beyond Horndeski, or so-called degenerate higher order scalar tensor series. What does it mean? It means that the equation of motion of these models, for example, beyond Horndeski, can contain the higher derivatives with respect to spatial coordinates, but temporal coordinates, the derivatives, are not higher than second order. For example, the Tost theory, the Lagrangian of Tost theory is has the following form. This is even more general theory, and you see that there are 19 terms in the Lagrangian. But what is important and interesting, that most terms are some combinations of covariant derivatives of scalar field, and only two terms describe the non-minimal coupling between scalar field and curvature. And again, we obtain that there are only two terms describing this non-minimal coupling. And what is important, that these terms qualitatively difference each other, because one describes non-minimal coupling with scalar field, and the other describes the non-minimal coupling between derivative of scalar field with curvature term. So, let me repeat once more that even the most general scalar tensor theory have only these two kind of terms describing non-minimal coupling. Okay, one can think that probably it's quite important and very deep sense in these terms. Actually, I believe that it's so, and in my short lecture, I will focus only on the theories with non-minimal derivative coupling. Non-minimal derivative coupling, and I will consider the simplest action of this form. So you see Hilbert-Einstein, Lagrangian lambda term, some usual ordinary ordinary, usual kinetic term, and a term describing non-minimal derivative coupling here. Also we have some potential of scalar field and some action describing the ordinary matter fields. Some comments. Lambda is cosmological constant here, and I will say that is bare cosmological constant because I don't know which cosmological constants we obtain as the solving the asymptotical describing asymptotical behavior of the universe. About this kinetic term, you see that if epsilon is equal to 1, we obtain ordinary scalar field, -1 phantom scalar field with negative kinetic energy, and if we in the simplest theory with usual scalar field, if we consider epsilon equal to 0, it means that there are no standard kinetic term, and your model is not dynamical at all. No dynamics for scalar field in this case. But in this case, when we have non-minimal derivative coupling term, there is some sense to consider this situation also. And actually, it's very important model when there are no standard kinetic term, and people consider these situations and obtain some very specific solutions for cosmology, for black holes, and so on. Okay, very important term and ingredient is this one. Eta is coupling parameter, but important, that is dimensional coupling parameter. So we insert in the physical model by hand new dimensional physical parameter, in fact fundamental parameter. And of course, any new dimensional parameter give us some new physics. It's obviously, and dimension is length squared. So because of this, we can introduce some notation plus minus some lambda squared, L squared, where L is some characteristic scale of non-minimal coupling. So plus and minus means that this parameter could be as positive, both positive and negative. Okay. It's field equations and quite complicated, and I just say again that field equations are of second order. People usually use this form to write down the field equations, and you can say that this is modified Einstein equations, but it's not so exactly, because you see that left part is geometrical part if you speak about Einstein equations, and right side part describe the matter, usual matter. But actually this term also contains geometrical values, curvature, scalar field, and so on. So it's just convenient form to present the field equations. Yeah. Okay. We can consider various situations, for example, compact astrophysical object, neutron stars, black holes, wormholes. But here we will speak about cosmological solutions and cosmological models for this theory. And first we consider isotropic and homogeneous cosmological models. And for simplicity, I will consider the following case, the following ansatz. No potential, ordinary scalar field, some perfect fluid, and Friedman-Robertson-Walker metric. Let's consider the following situation. And gravitational equation and the equation of motion for scalar field are given here. And because we have no potential in this model, we have the first integral for scalar field. This is first integral, and let me just say that psi here is phi dot, because no potential, there is no potential. Everything depends only on first derivative of scalar fields, so phi dot. This is first integral of the system. Okay, then let's use standard standard actions, made standard actions, and consider matter as a combination of non-relativistic part and relativistic part. So this is dust and radiation. And after this, we introduce some dimension-less parameters. Here it's quite convenient, and of course, these are dimensionless density parameters connected with curvature, not curvature, it's cosmological constant, curvature, dust, radiation, and scalar field. And after this, we obtain the following modified Friedman equation. And let me say, characterize this equation very shortly. Look at this. First, we will assume that lambda is positive, non-negative. It means that omega 0 is also positive, and omega 2 is negative, positive, or equal to 0 for specially flat case with constant negative curvature and constant positive curvature, respectively. And about this parameter, zeta. So this is dimensionless version of non-minimal coupling parameter. And you see that we can rewrite it as in the following form, as some ratio between characteristic non-minimal coupling scale and Hubble scale. So this is ratio of these two scales. Because of this, we can suppose that this parameter is very small, because physically it's normally to consider the situation when this scale is much more or less than this one. But it's not necessary for our aims. But anyway, you should remember this, that this is a ratio of two very important physical parameters of your model. Okay, in case when scalar field is absent at all, you just obtain the standard master equation of lambda CDM model. So you can ask me or yourself, is the standard cosmological model, Friedman cosmological model here? Yes, of course. Just say that no scalar field at all exists, and immediately you obtain the lambda CDM model. So the main difference is only with standard lambda CDM model is only in this term. Okay, anyway, but if you consider, if you include the scalar field in your model, but you consider the situation when zeta is equal to 0, so non-minimal derivative coupling is absent, you obtain cosmological model with ordinary scalar field. In this sense, it's well known that ordinary scalar fields behaves as a stiff matter. So it's also quite standard situation. Okay, you see that the modified Friedman equation contains h square, dimensionless Hubble parameter. H square here, h square here, h square here. Because of this, you can denote h square as y and rewrite the master equation as a cubic equation in y. It's just algebraic equation. It's just algebraic equation in y, where y is squared Hubble parameter. Coefficients of these equations are given here. Quite long and complicated, but it's important. And coefficients depend on all parameters of model and also depends on a scale factor. Remark is the following: if one obtains roots of this cubic equation, so roots means that h depends on a. So after this, you obtain you can describe the global cosmological, the whole global cosmological evolution of the universe using this very simple relation. So technically, everything is very simple. We should solve the cubic equation, but I personally, I just hate cubic equations now after working with this. It's because actually there are no simple interpretation of roots of cubic equations, and there are some imaginary roots and so on. But anyway, technically, if you like it, you can solve these equations and describe everything what you want. In this talk, I will speak about very specific thing. I will discuss turning points in the cosmological evolution in this theory. And you see that if you want to obtain turning point, what does it mean? It means that the scale factor reaches its extremely maximal or minimal values. It means that a dot is equal to 0, and it means that h squared is equal to 0. So evolution is stopped at this point. It means, respectively, it means that y is equal to 0 at some corresponding value of scale factor. So we are interested in specific roots of this polynomial, cubic polynomial, roots y equal to 0. And this polynomial has a root y equal to 0 if and only if this coefficient equal to 0 at some value a star. C0 is the following coefficient. If we equals these coefficients to 0, we obtain the following two branches of equations. This one and this one, because you see that this coefficient is actually factorized, and because of this we obtain two conditions. Okay. Some notice here that these conditions have no solutions at all in case when omega 2 is negative or equal to 0. So cosmological models with negative or 0 spatial curvature, there are no turning point at all. Okay, turning point, first condition. I have no time, so I try to be more faster. let's consider first condition. In the simplest case, when no lambda term, dust, radiation, no non-minimal kinetic coupling, we obtain very simply we obtain the following. And you see that in this case, because we believe that the special curvature is very small, this parameter should be also very small, and we obtain a squared very big. So it's very, very big because it depends like 1 over omega 2. So what does it mean? It means that we obtain 5 minutes, I know. We obtain this is turning point in the very, very far future. This is turning point. And because A is has a maximal value, this is turning point which our universe achieved its maximal size, and then after expanding begin to contract. Okay, and what is important, in general case you can check that in general case you can find some solution of this condition, and you obtain the A maximum as a function of all parameters of this model. Okay, but we have also the second condition. And again, let me say that the second condition appear only in the case when we have non-minimal kinetic coupling. It's a very essential part of this theory. And the second condition has the roots only for positive value of omega 2, only for positive curvature. And this condition, of course, can be self-trivial. So A star squared is given as follows. And where is it? So, because we believe that omega 2, the special curvature of modern universe is very small, and zeta is also small, we obtain that a minimum is very, very small. In dimensionless units, the modern value for scale factor is 1. So less than 1 means that early stage of the universe evolution. Okay, some turning point at every stage of universe evolution, and minimal value. What is it? This is bounce. This is bounce. And actually, what is very important, this value depends only on the product zeta and omega 2, and does not depend at all on cosmological term, on dust, on matter. And in this work with Stravinsky and Volkov, we call this situation as screening Hermdesky cosmology. So actually, the existence of bounce does not depend on cosmological constant, does not depend on matter filling, and so on. And this is very, very important. Okay, in this slide I just consider, because it does not depend on omega 0, omega 3, omega 4, let's consider the more simple situation just to describe the behavior near the turning point. And actually we can see that AH square goes to 0 as this value and A square goes to its minimal value, like this one. And evidently that we obtain the regular space-time geometry in the vicinity of this bounce. It's very, very good. However, we does not discuss the scalar field yet. We discuss only Friedman equation. But scalar field equation, we have a first integral, this one, and actually I show shortly here the dependence on time, and actually the first derivative of the scalar field is singular near the bounds. So we obtain some specific situation. I call this situation singular bounds because in my experience I met this situation first time, and we have a singular behavior of scalar fields when approaching to the bounds, but scalar fields is singular, but the space-time geometry is regular in this situation. Well, just because I have no time, I just show you some numerical calculations. So without any approximations, numerical calculations, zero meaning. Okay, this is numerical calculations for scale factor, and you see that in particular you can obtain, because you have bounds, you can obtain cyclic scenario of cosmological scenario of in this model. Okay, actually I can say many different things, but let me just finish with some conclusions here, and I should stop here. Okay.
Thank you, Sergey. We have 5 minutes, so. Oh, yes, please.
Just please a little bit loudly, okay?
Hello, can you hear me?
Yeah.
So the first question is, you are doing everything close to the Big Bang, right? So why do you want to divide it with the current Hubble constant? You could have just divided with the inflationary epoch or some energy scale, which is h, which is actually more relevant that time. That's my first question. The second question is, what energy condition are you violating?
First of all, let me say about inflationary epoch here. Let me say, because I have no time. We consider this model already from probably 2010, and the first interesting thing is that here we obtain the quasi-de Sitter plateau in all models. This is k equal +1, 0, -1, and in each model we obtain some plateau, and this plateau is in fact quasi-de Sitter plateau. So, and the size of this plateau, because it's because of this dimensionless values, actually the size of this plateau is depending on your parameters, could be as long as you want. Yeah. So we obtain initial inflationary stage here without any potential, because you see that I put potential equal to 0. So there is no, it's not necessary to solve the fine-tuning problem and so on. And it's a very interesting feature of this model. So we have no potential at all. This is kind of kinetic inflation. Yeah, but kinetic inflation which derives purely by non-minimal kinetic term. Yeah. And actually, I can show you the typical picture. H square equal to, this is asymptotic. This is asymptotic, and you see that h square is constant value and depends on 1/9 zeta. And you see that, well, I say this, so here we obtain eternal inflation, quasi-de Sitter behavior, and this factor equal to zero, equal to this value. And also quite important that there are no limit. Eta goes to zero. There are no limit because it's non-analytical. There are no analytical continuation to the situation when non-minimal coupling equal to zero. So of course I don't know if I answer your question or not.
The second question is about the energy condition.
No problem with energy condition at all, because we consider normal ordinary scalar fields here. So
But you have to violate some condition.
you see that first of all, I start my talk with the following statement: that what does it mean, this scalar field? Is it physical field or not? No, matter here describes by some other Lagrangian. So we do not consider any matter in this model. We consider we consider matter. I'm sorry. We consider matter as a dust and radiation, but dust and radiation is absolutely normal matter. Does not violating any energy conditions. What about scalar field? I don't know, because it's not physical field. It's just part of gravitational Lagrangian.
We have 1 minute for quick question, really quick question. So maybe just one quick question. So could you go back to the Horidinsky gravity where you wrote the epsilon in the kinetic term, right? Both positive, negative.
Go back.
Yeah, among the first slides, like Horidinsky gravity where you took the epsilon, right? The kinetic term. Very early. Okay. 5 or 6. Yeah.
This one?
No, 5 or 6.
Number 5.
Yeah, okay.
I have numbers. I forgot about it.
Yeah. 6 probably. Yeah.
Yeah.
Next. Okay. So point is that you took the kinetic term as 0, +1 or -1, right? Or phantom or this. So
maybe this one.
yeah, this one. Yeah. So I'm asking that you got the 0 because it is coupling with the G mu nu. So I'm asking that what is the dynamics of the scalar field even in this? Like what is the corresponding Klein-Gordon equation? Because you need a Delaunay, right? So could you just answer on that?
You see that you can consider the situation when epsilon is equal to 0, but you have the following modified kinetic term, modified by non-minimal coupling between derivatives.
Okay. So that would act as a Delaunay. Oh, okay.
Yeah.
Sure. Okay,
So,
thank you.
so if you have this term, non-minimal coupling, of course you have no dynamics at all.
The last quick question. I'll give you extra work.
Hi. So can you comment on what this theory could say about?
Just louder.
Okay. Yeah. So can you comment on what this theory could say about black holes? If something about
You see that it's very, very long question, because
Okay.
I have no time even
okay, I'll
to
meet you
discuss
after.
cosmological problem. I just comment. You can find in the literature lots of works concerning the black holes and wormholes and even neutron stars in this model. And actually, this model is quite specific, and there are quite specific properties of these compact objects in this theory. That's all what I can say, because no time. But I can just repeat that there are, and not several, but many investigations concerning black holes, wormholes, neutron stars in the theory with non-minimal derivative coupling. And for example, there is a very special model when epsilon equal to 0, without no standard kinetic term, so-called stealth black holes, which imitate the Schwarzschild solution. Yeah.
All right, thanks.
Thank you.
We'll move to the second talk. Speaker
Help me,
is
please.
Shankaran Narayanan. He'll talk on gravitational wave memory as a tool constraint cosmological models. Yeah, sorry, 5 minutes and 5 minutes for Q&A.
Shall I go? I might have, because no. Slide changer. ये नहीं होगा, इसमें नहीं है, एक्स्ट्रा नहीं है. ओके, एक और नहीं है, दूसरा. हाँ, उसमें होगा ना. या. I think दोनों ये भी चार्जर भी डला है ना. या. आ रहा है ऊपर. Slide changer हो रहा है. Oh, good. I would like to thank actually Sami for inviting me and forcing me to be here. So what I wanted to talk to you about is two aspects. One is constraining cosmological models and gravitational wave memory. So before this, I just want to have a precursor to what we actually what I want to talk about. So we all have binocular visions, right? So we have two eyes, and each eye looks at the object slightly differently, and our brain processes it. And then we get a kind of a 3D vision about the universe, so about what is happening around us. So what I want to look at is, we have been, for the last 400 years, we have actually been seeing one eye in the cosmology, which is using electromagnetic wave, and we have been seeing the universe in a particular way. Now, we have, for the last 10 years or so, we have another eye, which is the gravitational wave, and we actually been using this, we have been able to make some interesting observations about the universe. So now what I want to ask is, if you now use both these things, basically electromagnetic and gravitational wave, how does it help us to constrain the cosmological models, basically? So I think the work is basic. What I'm going to talk to you about is basically the new paper which is there in the archive, and it is still under review. And this is actually, it's also based on an earlier paper, which is published in PRD, and it is done with Sushmita Jana, I think she's here, and Indranil Chakrabarti, who's a postdoc. Sushmita is actually a PhD student. Fine. So the talk is going to be, I'll give a brief review of the tensions, because already people have talked about it. So I just wanted to put it in a perspective in the two-eye concept. So I just wanted to spend a couple of minutes on it. And then I'll spend a lot of time on this gravitational wave memory and what are the current approaches and why we have to come up with something different. And so I'll do a kind of a detour about Eulerian versus Lagrangian observers. And finally, I will not get into the details, but I'll get the final equation and I'll look at the implications for cosmos. Okay, fine. So I think, sorry. That is, it's really gone. Yeah, fine. So I think the last 2 days we have been actually hearing a lot of talk on tensions, but I just wanted to put it in a perspective because I wanted to see that where we are actually heading to. So we have two kinds of measurements. One is the local measurements and one is the cosmic measurements. The local measurements are through the C5s and TRGBs, and the cosmic measurements are best primarily from CMB, and there is a 5 sigma deviation, which is what we have been hearing a lot. So the way to think about it is, the way I think about it is that you have a car and you drive the car, and the car speedometer is telling that 74 kilometers per hour. Now you calculate the total distance the photon has taken or we have taken as in the car and divide it with time, and that gives you 67 kilometers per hour. So now, so you can ask two questions, whether the speedometer is faulty or odometer or the clock itself is faulty. So you can think about it in two things. So basically we want to ask a question whether the speedometer is faulty, assuming that all these observations are right. So whether the speedometer is faulty or the odometer or the clock is faulty. So we cannot just do it with electromagnetic waves, we need with something else. And that's basically where the gravitational wave comes in. Fine. Okay, so I just wanted to put this in perspective. I don't think so anybody had this slide. I think this is a nice slide from Friedman 2024 paper. So the interesting thing is, we always thought that the reason why there was the cosmic tensions, or actually we see it, is because the errors were large. So we were never thought that it is actually going to be, it is not going to disappear. It's always there. So as you keep going, as the observations become precise, you see that this is actually diverging. So I think about it like in the case of quantum field theory in 1940s, when we did first order approximation of scattering, we all got it right. But after that, when you look at it in the higher order terms, we always get divergences. And that basically, think about it like, basically you can think about it like something new physics can actually be interesting. Okay, so I'll just mention this. So the SH tension is also there. And this is again measured with respect to 8 MPC. And if you take it in two different observations, one for the CMB and one with the low redshift probes, there is a 3 sigma deviation. And again, what I want to drive is this, all these observations are based on electromagnetic spectrum. Now what happens to the gravitational waves? Okay. So now, luckily we had an event which is in 2017, and they got a binary neutron star coalition, and they could actually measure the luminosity distance, and the distance calibration could be precisely done because they used precisely coming from GR, because there is no other deviation from GR as far as we know, and the electromagnetic observations provided a redshift. So then we can actually get a luminosity versus redshift, and then we actually get with a error margin, and it turned out to be exactly at the center, around the order of 70 or so. Fine. So now we are expecting that in the next 10 years or so, when more observations of LIGO comes in, and also ET, the Einstein telescope and Cosmic Explorer are going to come up, we are going to see that there are going to be more and more observations, and they're expecting that this error margin which they have got here is actually going to be narrowed down. Fine. But this is only going to discuss about the background cosmology. It's not going to tell us anything about the perturbations itself, and which is where the S8 sigma, the sigma tension comes in. And so the question is whether gravitational waves, which are responsible also for further gravity, can it actually be useful to this? And that's where the gravitational wave memory comes in. So what is memory? Memory is actually a kind of a bad nomenclature, because people think that we are actually doing something, since it has gravity seems to have something extra compared to the other 4 forces. This is actually a bad nomenclature, but it's actually, when I explain it, will be clear. So we know that if I have an asymmetrical distribution of masses, and if it collapses, for instance, you will get a gravitational wave. Now when the gravitational wave emits, when the body emits gravitational wave, the gravitational wave itself has asymmetries. They are not symmetrical, because you have a plus polarization and a cross polarization, for instance. So they will actually be emitting asymmetries. Now we know that gravity carries energy. So this energy will also can, in principle, since it's asymmetric and it carries energy, it also can create secondary gravitational waves. But of course, this will be weaker. Fine. Now these secondary gravitational wave, when it passes through another region, set of region, they will create a tertiary which is weaker than the secondary, and this keeps going ad infinitum. And if you look at it, if you have a gravitational wave event, like for instance, whatever we have seen, binary black hole collision, you will actually have oscillatory signal, which is here, superposed on it, you will see something which is basically secondary gravitational waves which are generated, and that would actually give you a kind of a permanent alteration of the spacetime. That's the reason why they call it as a memory. And you can see that if you don't have a memory, then you will have a mean which will be like this, 0. But if you have a memory, then you will actually settle down, the final oscillatory signal will settle down into a DC level, which is slightly above this thing. Fine. So this has been done, which people have been doing, starting from Zeldovich, and I just wanted to explain what we actually people do it. Fine. So the way to think about how do I envisage memory? So let us consider two particles, P1 and P2. They are initially separated at a distance zeta 0, and we throw the particle, and this is actually moving freely with respect to I put it as Earth, but it could be anything. So it's just having a gravity on it. Fine. And we all know what is the geodesic deviation equation, which is all known, and zeta is basically some vector which I'm interested in. Now let us assume that there is nothing else which is present except a flat space-time, but there is actually also have a gravitational wave which is passing through it. Fine. And I'm assuming that the gravitational wave is weak, so h mu nu is far less than 1. Fine. So let us do the standard traceless transverse gauge and do all the calculations. Then in the laboratory frame, and this is where the things comes interesting when I'm discussing later. So this would actually give rise to this. So this is your expression. There is nothing hunky-dory which I've done. It's just a simple 101 and GI. Fine. Now, if you think about, so what happened is that we didn't have gravitational waves every time. We had for a narrow period, we had a gravitational wave like this. But initially the space-time was Minkowski. Later on, there was the Minkowski space. But what happens is that suddenly, at a small region for a finite period of time, there was actually a gravitational wave. Now you can do the calculation. This is basically the Zeldovich paper, 1974, and you calculate and you will get a linear term which looks like this. Okay, because you have asymptotically you have no gravitational wave, but you have a gravitational wave for a period of time. So then you can actually calculate what happens. So now the way to think about it is that asymptotically it's Minkowski at t equal to 0 and t equal to minus infinity and t equal to plus infinity. Suddenly there is a small deviation which is coming in because of the gravitational waves, and now you can ask a question, what is the total deviation delta zeta high? So basically the way to think about it is this. So we ask a question, this is the zeta of eta. Now we are interested in what is the delta zeta which is there, and that delta zeta is actually proportional to how much of gravitational wave which has actually passed through. Of course, if the gravitational wave itself is small, it's going to be extremely weak. But the question is, if the gravitational wave is very strong, and if you do it in a curved geometry, what happens? Basically, that's what we are actually heading into. Fine. Okay. So what is the status of the gravitational wave memory itself? Most of the analysis, actually I can say 99.99% of the calculations are done in asymptotically flat space-time, and because the calculations are easy, and people have derived these expressions very well, and they know that it actually goes out as 1 by r. It's a radiative term, and it is 1 order lower compared to the usual gravitational waves. Of course, it's because of the fact that these are secondary waves, so these are not the primary waves. So most of the analysis is basically done primarily after the Strominger's group, which basically proved that there is a kind of a triangle or a trinity of things, asymptotic symmetry coming from BMS, memory effect, and soft theorems. These are all actually linked to each other, and that's basically most of the effort is primarily because BMS is on asymptotically flat spacetimes. This infrared triangle has actually been the driving force for calculating memory in, for instance, for asymptotically flat spacetime. Now, the interest is that if there is a physical effect, which you see it and GR predicts, can we use it for other spacetimes and see whether we can actually gain some insight into it? That's basically what we are interested in. Fine. Okay, so what are the questions which we want to do before we even go into the calculation? First, what is the key ingredients we need to calculate for an arbitrary spacetime? So basically, what are the dynamical equations? So for instance, Einstein's equation, Einstein's equation plays a role. As I showed you, most of the calculation was done using geodesic deviation equation, so it doesn't use anything of Einstein's equation. So if we want to ask a question, what does the dynamical equations actually, how does it play a role? How do we actually predict it? What role the background geometry plays? Because till now all the analysis was done for asymptotically flat spacetime or a flat spacetime. So we were interested to how does this actually affect background geometry effects? How do we relate the memory to the geometric and physical quantities? These two are actually related to this. And can we actually finally use this to study cosmology? Whether gravitational wave cosmology, now gravitational wave astrophysics is actually a big thing. Whether gravitational wave cosmology can actually be a big thing in the next 10 years or so, how do we actually do it? Those are the primary questions. So basically what I'm going to do is I'm going to cut short these discussions because these are details, but I'll be spending a lot of time on the question 3 and question 4. Okay, so again I want to give the setup. So we will consider some black hole or neutron star collision, which basically collides and it creates gravitational waves. And so basically this is at some redshift, very high redshift. We don't worry about what redshift it is. And so this is your gravitational wave. Because we know that the gravitational wave is transverse, I have represented it as a 2 surface. Now it passes through, and we are interested to know how does the gravitational wave memory, which is basically used, how does it change as a function of redshift? Fine. Now there are 2 things to this compared to electromagnetic wave, because I've been comparing electromagnetic and gravitational wave. Now unlike electromagnetic waves, so the gravitational wave and electromagnetic waves are going to be emitted. In the case of neutron star, we know that it is emitted. Black holes, we have not much of information about it. So both of them will be emitted and both of them are going to traverse and reach us. But the gravitational waves, we know that it interacts with all forms of matter, irrespective of it. Dark energy also interacts with it. Dark matter also will interact with gravity. So unlike electromagnetic waves, gravitational waves will interact with all forms of matter. So and then the memory, which we are actually going to evaluate, which will also contain information about not just about the baryonic matter, it will also contain information about dark energy and dark matter. Fine, that's the key thing. And the second thing is, since gravitational waves interact weakly with all forms of matter, unlike electromagnetic waves, the gravitational wave memory will only contain information about the background geometry. So in the sense, whenever we calculate, for instance, when we do CMB, large L's, we will have problems because you will have other kinds of noises which comes in. Here there will not be any noise because the gravitational wave will interact very weakly, so there won't be any noise. What you are going to get is a clear, clean signal, okay, if you measure it. Okay, fine. So before I actually go into this, we want to look at what is the detection prospect itself. So as I mentioned, there is a detailed calculation in the case of asymptotically flat spacetime, and people have shown that the gravitational memory is 1 order lower. For instance, if you measure 10 power minus 23 a signal right now from a black hole collision, then you will get up to the order of 10 power minus 24. So that is basically the signal which you will be able to get. Fine. Now this is actually a nice picture from Hall 2022, where he basically shows the left side is basically what is the capabilities of Cosmic Explorer and Einstein telescope with respect to neutron star binary collisions. And on the right side is basically the black hole collision. So as you can see, the neutron star collision in principle can be up to redshift of 10. A Cosmic Explorer or Einstein telescope can see, and the black hole collision up to a redshift of 100, okay, which none of the electromagnetic objects can actually see. So in that sense, we are actually going to be a much larger distances. Fine. So we should be able to witness at least huge number of events in the next by 2040, we should be able to see a lot of events like this. Fine. So the question, again, I'm reiterating it, how significant is the gravitational memory in an arbitrary space-time? Because this is only done for a flat space-time. And what new information the gravitational memory will tell us about the late time. Okay, so now I'll just go to the setup. So now I'm going back to the paper, which is basically in the archive, which I mentioned in the first slide. So the setup is basically this. Let us assume that t less than 0, t0, that's some time t equal to t0. The spacetime is non-radiative, so it is basically FRW, Schwarzschild, everything is non-radiative spacetime. So we look at all those spacetimes. So basically so in this case I put it as a FRW. So we will consider a spacetime which is non-radiative and doesn't have any gravitational waves below for t less than t0. At t equal to t0, there is some binary collision which happens. Black hole binary collision happens, and there produces a gravitational waves at time t equal to 0. Now the gravitational wave along with the electromagnetic wave, they will travel from t equal to t0 to t equal to t1, and this is where we have a detector, fine. And this detector is supposed to see this. Now, please remember, since the gravitational waves as well as electromagnetic waves are transverse, so basically all the effects can be actually encapsulated in this 2 surface, which is perpendicular to it, fine. So now, so it encodes all the information. Now, basically, if you can calculate what kind of deformation this 2 surface will actually happen, then in principle we will be able to understand what is the effect on the gravitational memory. So we will have 2 components. One is going to be the oscillatory component and one is going to be the memory component. So what we are actually interested is basically the memory component here. I am actually going to ignore the oscillatory for the present. Fine. So basically what we want to do is we want to integrate the entire effect coming from t equal to t0 to t equal to t1 and calculate what is the total effect which happens on the 2D surface. Fine. So basically, if you can actually have a formalism which can evaluate the 2D surface, the effect, total effect on the 2D surface, then we are actually through. So we will be able to do the calculation. Fine. So I just wanted to do a detour before I actually go into the calculation because this is important. So if you remember, all the calculations were done with respect to a flat space-time and where there is an observer who is sitting somewhere, right? It's a static observer. All the calculations are done with respect to 2 static observers who are actually freely falling. Now those are basically, if you look at it in the language of fluid mechanics, those are basically Eulerian observers because they are all static. We can always assume a static observer and do the calculation. This is what we do for most of the analysis in black hole physics. Fine. But however, if you want to apply it to FRW, for instance cosmology, we know that we are actually flowing along with the time. Fine. It's like this observer. So the observer is basically sitting on a boat and there is a free stream which just pushes the observer to go around. Fine. So we are actually these observers, we are not these observers. So we have to have a formalism to actually do the entire calculations in the Lagrangian formalism, not in the Eulerian formalism. Okay. And we know that our usual FRW is very well defined for that. Basically what we do is we do everything on a 3 space which is orthogonal to the world line, and then what we do is we basically split the FRW space-time into time and space, and a squared of t is basically the expansion parameter, and then we calculate all this, right? But then if you go back 3 slides, what we say is that we are not interested in the 3 space, but we are interested in the 2 space because that is what is actually important to calculate the memory. So basically, since we are interested in the 2 space, so 1 plus 3 decomposition is actually not a very useful thing. We need to further divide the 3 space into 2 space and another space, fine? And that is actually also developed actually primarily by Ellis and his group. So what we do is we have 1 plus 3 where 1 is time and 3 is space. So you further decompose this into 1 plus 1 plus 2. So what is this 1 plus? So basically we have a time-like observers. So these are the basically Lagrangian observers. So we will go through with the Lagrangian. And we already mentioned that with respect to these observers, we can define a 3 space which is HA. Right? Now what you do is you divide the space and say that there is a unique spatial direction. So for instance, Schwarzschild has a unique spatial direction which is the radial direction, right? And theta phi is basically orthogonal to r. So you take a unique spatial direction. In the case of FRW, if I write it in the spherical coordinate, again I have a unique spherical direction, unique spatial direction which is r, and then you will have basically theta phi which will be the 2 surface. Fine. So what you can do is you divide the 3 space into a unique spatial direction, think about it like a radial direction, and then a 2 space which is theta phi. Fine. So I have notation which is HAB which is now 3 space. I have a NAB which is basically a 2 space. Everything I am writing in 4 vector notation, but it can be shown that it is only contributing only the 2 space. Okay. So you can divide this calculation. So you do the same thing. Now what you can do is you can ask a question, what are the physical quantities or the dynamical quantities which you are interested? Can you all write it everything in terms of this? You can write all the quantities, scalar, vector, tensor quantities are all there. I am not going to go into the details because that would take a long time. But you can always write down any physical quantities, like how you do in the ADM formalism, you write everything in terms of the Ricci scalar in terms of three curvature and the extrinsic curvature and everything. So you do the everything here, everything with respect to the 3 space, and then further divide it into 2 space. So all these quantities can be written. Fine. Okay. Fine. So then, so we have a system where we have actually been able to do the formalism, but now we need a space-time in which we want to do the calculation, right? We don't want to just do it for FRW, but we want to do it for a more generic class of spacetimes, which will actually be useful. And this spacetime is also exists. It's again done by Ellis for a long time, and it is referred to as a LRS. LRS refers to locally rotational spacetime, symmetric spacetime. Fine. So the idea is that since we are going to do everything with respect to Lagrangian observers, and we are considering a perfect fluid with a flow which is E-wave. Now, this is very natural for us to do everything in terms of Friedman, Robertson, Walker, because that is what our brain has been trained to do this. But this is what Ellis argued in 1970s, is that FRW is just a very specific class of these spacetimes, and you can construct various generic spacetimes which will all satisfy. We can also represent it in terms of a perfect fluid flow. Fine. And so since we are interested in non-radiative, so we are looking at something which has a Weyl tensor which is 0. So I said that there is again a preferred direction, and all kinematical and observable quantities are symmetric with respect to this radial direction, which is x, which I have represented as. Now, interestingly, LRS includes many spacetimes, Schwarzschild, LTB, cosmological spacetimes, FRW, Kantowski-Sachs universe, everything. So if you look at this review article, it has all possibilities. And LRS is further divided into LRS 1, 2, and 3. And we are only going to look at one spacetime, which is LRS 2, because it is advantageous, because FRW is corresponding to this. Fine. So we are looking at, so basically, we wanted a framework to calculate gravitational memory, which will be able to account for the transverse direction, and which will be able to calculate with respect to the Lagrangian observer. So what I've kind of told you is basically saying that LRS spacetime with the 1 plus 1 decomposition actually serves this purpose. Fine. Okay. So now we'll go back to the main calculation, and I'm not going to go into the details of it. So I wanted to mention the approach which we are doing. We are considering there is no, as I mentioned, LRS2, Friedman, Robertson, Walker corresponds to LRS2. I'm just sticking to LRS2, but the analysis can be extended to other spacetimes as well. So for t less than 0, there is the spacetime is LRS2, and there is a gravitational wave which comes and disturbs the spacetime and alters the spacetime from LRS2 to LRS2 plus something. And what we are interested in is the 2 space, because the NAB is the 2 space now. And this, we are interested how does this 2 space is evolving as a function of time from tau equal to tau naught to tau equal to tau 1, and evaluate the total memory which is actually evaluated. So basically the total disturbance is what we are interested in. So the total disturbance is basically delta NAB, because that is the change in the 2 surface. NAB at t equal to minus infinity, I'm just calling it as t equal to minus infinity, and t equal to plus infinity, that is where we measure. So t equal to minus infinity is when the gravitational wave event happens, and t equal to plus infinity is when we actually, in the detector, we actually measure it. So delta NAB is basically the total change in the memory. You can show mathematically that this is nothing but the Lie derivative, Lie drag along this curve, and you can calculate what is it. Okay, so I am not going to get into the details, but just the calculations can be done. Fine. So after all this calculation, we get a master equation which looks like this. Okay, so just to highlight the, just a minute. I think there's no battery. So I just wanted to mention that the NAB is also related to sigma AB, which is corresponding to the shear on the 2 space, on the 2 surface. Fine. Okay. So what you have an equation where sigma AB dot plus some theta, which is basically nothing but corresponding to the Hubble parameter, and mu and p are basically the energy density and pressure of the background spacetime, because of which the FRW is there. And then G bar AB is nothing but the oscillatory signal which generates the memory. So for instance, if there is no signal, if there is no mergers, they will not have any memory. If there is no gravitational wave, because the gravitational wave is the one which is actually generating the memory, so you need to have a source term, unlike what we do in the case of perturbation theory in cosmology. So you need a source term to generate the memory. So if the source term is 0, you will get 0. Okay. So the memory will be 0 if the source term is 0. So the source term is actually crucially tells you how does the memory behave. So basically given this, you will know what the memory is. Fine. Fine. Now you can, so just to think about it, if I set this equal to 0, you will get two terms. One is basically a decaying contribution, one is a growing contribution. Fine. So this is actually crucial, because if I have a universe where mu and p is basically given by matter dominated, then your homogeneous solution will actually be very different. If I have a dark energy universe, then this homogeneous solution will be different, because it will have a different growth factor. So this is actually the most important point of this. If you have a mu and p, because it's the 2D shear which I have calculated, it depends on mu and p. So it is actually depends on how different it is in a dark matter dominated epoch and a dark energy dominated epoch. So if I have a mu p, which is actually because we know what is mu p is during the matter dominated epoch, so this will be very different. Now if I have for a dark energy dominated, mu and p is going to be very different. So hence there will be actually a difference in the way in which the growth of the memory is attached to, depending on what background we have. Fine. So this goes back to the fact that the memory will include all the information about what kind of matter field are present in the FRW universe. Fine. So the different forms of the fluid can lead to different growth. So the point is that given a primary gravitational wave signal, we will be able to do this. Fine. So what we can do is, we know this has been going on for a long time. People have been studying this shock wave, basically something like a shock wave, where people can show that what kind of source which can give rise to a shock wave, and people have modeled it and understood the gravitational wave corresponding to it. So these are basically done by Eichelberg and Sechsel in 1970s. Then Drey and Tooft actually did it later on, and Koss is actually something which recently did it in 2012. Fine. So one can actually calculate all this, and we can substitute what should be the G bar AB corresponding to a gravitational wave, which is like a shock wave, basically because it just happens in a shock, and then goes at a speed which is c. Fine. So to cut long story short, so this is going to be for a plus polarization. I'm only going to go for plus polarization. You can do the same thing for other polarization. So once you do this, this is basically what is the cosmological memory is. So there are two, three factors which I wanted to mention. So this will depend on what is the gravitational wave, incoming gravitational wave signal, which generates the memory. So the G bar which I wrote down, that basically tells what should be. So I just modeled it with respect to this. And rho is given by, this is basically the cosmological factor, or what is called because of the fact that the universe is expanding, so the gravitational wave actually should decay away with a factor. So that is the cosmological factor which decays. Now the most crucial term, which is actually this is the key feature of our calculation, is this factor, which is basically the integrated effect. So this factor was missed out by all the papers, including Wald, where what they did is they just had these two terms. They actually ignored this because they just didn't calculate the entire calculation. They just, whatever they did it for a flat space-time, they just approximated and said that this should be the case for FRW, and then we actually said that this is what it is. Fine. So we can integrate this expression. So we'll have in three different terms. One is the gravitational wave source amplitude at Earth, which we can actually determine from the oscillatory signal. And this is basically the cosmological background, which is actually determining how much of it is actually decaying away. And the third is basically, what I mentioned, is the integrated effect. So depending on the model, which is h of z, you are going to have a different features. And hence you will have something. Now the important feature is, when I put this Zs is equal to 0, your memory should be 0. If it is happening at a very short distance, so for instance, let us assume that there is going to be a black hole merger within our own galaxy, right? It is very hard. It's going to be 1 in 100 years. But even if it happens, then it's actually going to be nothing. There won't be any memory signal. You will only see a supernova or something, but you will not get any memory because there's an integrated effect, so you will not get anything much. But if it is actually going to happen for a very large distance, as I will show in the next slide, you will actually see the memory signal is going to be very large. Fine. Okay. So now, I don't know whether Anjan is around. Okay, he's there. Okay. So yeah, so this is basically, so what we did is we tried to take a model which is a very minimal model than lambda CDM. I think Anjan mentioned it in the yesterday's talk also. So we considered a model for the cosmology, the late time cosmology, which is h of z is nothing but h0 omega m 1 plus z 2 by b. It's exactly the same parameter which I think he used, and 1 minus omega m. Omega m is basically the matter dominated, the content for the matter, and this corresponds to the dark energy or lambda, depending on what you want. So as I think he mentioned, when b is equal to 2 by 3, it will correspond to lambda CDM. When b is not 2 by 3, it will correspond to some minimally evolving dark energy. Fine. So what we did is we calculated the integrated memory, the integrated effect. So this is basically the one which is in the previous slide. So this is what we are actually evaluating, that is in the y-axis. So the y-axis is basically this with respect to the signal thing, and what is in the x-axis is basically redshift. Okay. So as you can see, if the redshift is 0, you should not get any memory. You will only look at the top plot. I'll discuss this lower plot later. So as you can see, this part is 0. When the memory is when the redshift is 0, you will get 0 memory, as I mentioned to you. As we keep going to larger and larger distance, the larger and larger redshift, you will see that the effect is going to be very different, depending on what model cosmology you have. So for instance, if b is equal to 2 by 3, which is basically the brown curve, which you can see, so you will see that is actually going to be very different compared to, for instance, b is equal to half, which is on the top, or when b is equal to 3/4, which is on the bottom, basically. Fine. So the thing is, so depending on the cosmology, the memory signal is actually going to be very different. And for a short distance, if the redshift is very less than 1, all the three will have a very same effect. So that you will not be able to distinguish with respect to for instance, the current LIGO and Virgo will not be able to distinguish it, because the memory signal for all the, I'm just doing a simple model. So for all the models, there is no significant effect, because the amplification factor is very small. But as you go to higher and higher redshift, for instance, if I have a signal, if I detect a signal which is at a redshift of 0.01, which is where the neutron star binary event was, and if that signal will correspond to 0.003. But if the same event would have happened at a redshift of 4, for instance, which we will not detect it now, but it will be possible in the case of the next generation, now you will get a signal which will be 0.621 in some units, which is some normalized units. So you get an amplification factor which is 180 times. Fine? Yeah. I'll take 2 minutes, sorry. So you will get, so what I'm saying is that, so if you take it, you will get a large amplification factor from a very large distance. Okay. So now what we did is we just took a derivative of the signal, and if a second derivative of the signal, and asked a question, how does it actually behave as a function of redshift. So as you can see, the lower redshift, so there is actually a dip which happens depending on what b is equal to what b you have. There is actually a minima which actually occurs. So which kind of tells what kind of transition it is. Now, just to tell you that for this to actually do, we need a lot of events. We need at least 50 to 60 events to have a plot and figure it out that there is actually a dip. So for instance, if I have similar kind of, easiest thing is the neutron star, because they have very similar masses. So if you have such an event, then you will be able to roughly know that the masses are roughly the same, and you can figure it out what kind of dip you will get. And this dip will actually be dependent on what kind of model you have. Okay. So depending on this parameter b, we have a different. So in that sense, it's actually a pretty good tool to do this. I'll just wind up in the next slide. So basically what I've shown is that the integrated cosmological memory is a nice thing, and it can actually be useful to look at different models. Now I just want to add one small thing which is important. Basically, if you look at this Pauline et al.'s paper in 2023, they suggested that to solve the sigma 8 tension problem, one has to look at, if you introduce a drag in the dark energy dark matter transition time, then that would actually be helpful to solve the sigma 8 and that A0 tension without affecting the early probes, basically. Fine. So this is exactly what we are trying to say. So if you can identify the transition epoch, which of course depends on what model you're looking at. So for instance, lambda CDM has a different redshift at a different epoch in which the transition can happen. And if I have a dark modified gravity, you'll have a different epoch. So each of this will have a different epoch, and that would actually be useful. That's basically what the Pollitt et al.'s calculation was. So what we are trying to say is that the memory, the gravitational memory is actually a pretty good tool to, in principle, to identify this transition. Fine. So, so these are basically prospects which I will actually stop if I can take some more questions.
Just I would like to know, you discussed about the plus polarization. So with the cross polarization also similar thing?
Yeah, we have not, yeah, it's very similar, but it will have the same feature. So the thing is, we know by, in the case of GR, both the modes of polarization are equally emitted. So you have to just calculate one of them and you will get the same answer. But this is not the case for other theories. For instance, modified theories will not be different. It will be very different calculation. But since this is just a proof of concept, we wanted to do it for one. But we can do it for the same thing for others.
Yeah, so I'm not very convinced that how you can distinguish model between, I mean, like let's say lambda CDM and this, the spalling model of dark matter, dark energy interaction. Because at the end of the day, all the effects comes from the background. Because the integration just takes in that background, HZ, fine?
Right.
And I can have an HZ which gives you dark matter, dark energy interaction with some model without any interaction, fine? So
No, there is no interaction, no? There is no interaction we are talking about. We are talking about the H of Z.
Yeah.
Huh.
So
this
the
is your H of Z, right?
yeah,
I can
so
add
the-
any H of Z in this.
Yeah, so it can only distinguish model at the background level. I don't understand how it can increase, how it can decrease models at the part-up level. Because
No, so the perturbation equation, so what I am showing is that the memory equation which I have got is basically a perturbation equation. This is a perturbation
no,
equation.
that's fine. But if you go to ultimately your observable,
Yeah, but what I am measuring is the perturbation. What is the memory which I am observing is the perturbation.
yeah, that's
Gravitational wave perturbation.
No, that's fine. But if you go, yeah, so your n, what is the expression of your n? That
Of course, no, because that is true for even our cosmology. All my perturbations are depends on the background quantities.
yeah, so
this is
that
true.
quantity that you have, that 1 plus z, that integrated quantity,
Correct.
that only depend upon the background age, fine?
Yeah, of course, that is true for even for perturbation in cosmology and inflation also.
Yeah, no, that's fine. But in inflation, there is also in the right-hand side, there is a source, fine.
Right. So there is a source here.
But that source is coming from the primordial gravitational wave.
No.
So what
This
is
is
that
basically the supernova, sorry, any even supernova or anything, black hole merger, neutron star merger, you will actually get the oscillatory signal from them.
No, that's fine. But
That is what we are interested in. So once you have the oscillatory signal, you want to use this, process it and try to see what kind of amplification you will get.
yeah, that I understand. But
Sure.
what I'm saying is the perturbation that we are talking about is basically the dark matter perturbation, fine? That
No,
is not
not
here.
dark matter. There is no matter.
There is
It's
no
a
matter.
gravitational
Yeah,
wave perturbation.
yeah, exactly. So the fact is that I mean that is all the extra that amplification that you are getting through this thing. It depends upon the age.
Correct.
And I can have a model with a no. I mean, with the age, it's very interesting. But only thing my comment is that it's actually distinguished model at the age level. Fine. At the
No, what I said is that in my first slide, which I said was basically to use perturbation to distinguish cosmological models, which is basically background models. We are not talking about, I am using the perturbations to distinguish the current NSNS which gives you a constraint on this thing, it only looks at the luminosity. What we are doing is an integrated effect, because the integrated effect comes in because, okay, I think this doesn't work. One minute. See, this perturbation contains the background matter. So that we are integrating over. It's
Yeah, so-
something similar to integrated Sachs-Full effect.
Yeah.
Exactly that.
So at the end of the day, my observable is that let's say I have defined this NS or black hole merger happening
Correct.
at different redshift,
Correct.
and I can probe up to higher redshift. Okay,
Mhm.
and I have all those events.
You have to collate all the events.
Yeah,
yes.
all up to redshift 10, and then I calculate the gravitational memory effect from there
Correct.
for each thing, and I see the study, and if I go to the higher redshift, then I start seeing the deviation from between models.
So yeah, there is one more added problem. The problem is current LIGO, even many of those things, they ignore the memory because they are not going to look at any memory. But if you introduce memory into this, your parameters which you have got, for instance, the masses, chirp mass, and other things, inclination angle will all change.
Yeah.
Because it all depends on what input you give.
Yeah.
So what I'm saying is, if you go for higher and higher redshift, you have to be very careful about what you are actually inputting.
Yeah, so
The
that-
Bayesian statistics.
Okay, we can discuss later.
Yes.
Shall we close the session? Then we can continue after session. So, thank speaker again.
Thanks.
Thank you also, Sandy. Any announcement?
Yeah, there are two announcements. We will quickly head for lunch now.